Hello, everyone. Welcome back to the afternoon program. The first invited talk in the afternoon is going to be given by Professor Yann LeCun. Professor Yann LeCun is Vice President and Chief AI Scientist at Facebook and Silver Professor at NYU. He is the recipient of the 2018 ACM Turing Award for conceptual and engineering breakthroughs that have made deep neural networks a critical component of computing. He was the founding director of Facebook AI Research and the NYU Center for Data Science. He is a member of the US National Academy of Engineering, a fellow of AAAI, the recipient of the 2014 IEEE Neural Network Pioneer Award, and the 2015 Parmy Distinguished Researcher Award. The title of Yann's talk is SSL, an energy-based view. Let's welcome Yann.
Thank you, Peng Tao. Thank you for inviting me. It's a pleasure to be here virtually. So I'm going to do something a little unusual, which is I'm actually not going to use slide. I'm going to give a Blackboard talk, or rather a virtual whiteboard talk. So first, short intro. As Jitendra said earlier in the previous session, common sense is a collection of models, not just a set of facts. And I think that's a really important point. He and I have been discussing this, of course, over the last several years on multiple occasions. And what I think is striking is that humans and animals seem to learn a lot about how the world works, mostly by observation. And this is a type of learning that we cannot yet reproduce in machines, and that a lot of us in working on self-supervised learning are trying to reproduce. So there's really two purposes of self-supervised learning. And they are different from the one that Alyosha Efros talked about earlier. I mean, not that different. The first one is to learn representations and thereby allowing us to basically train a system with a fewer number of labeled samples or fewer number of trials if it's reinforcement learning. So that's the first thing, sort of learning representations in a task-independent way. And then the second thing is also learning world models. So basically learning how the world works and learning to be able to predict what's going to happen in the world as the world evolves, or because we're acting on the world, so we can plan ahead, which is really the point of the quote that Jitendra showed from Kenneth Craig. So let me share my whiteboard, if I may. Here we go. I hope you see that. Okay, so self-supervised learning really, I think, should be kind of generally defined as learning to fill in the blanks, right? And we've seen a lot of examples of self-supervised learning over the last few years. Probably one of the most astonishing success of it has been in natural language processing, where we see, BERT-like architectures that are pre-trained to essentially predict missing words in a piece of text. So it's really learning to fill in the blanks. Several years ago, I got interested in video prediction for that reason. Can we learn arbitrary high-level concepts about how the world works by basically training a machine to predict what's going to happen in the world by just predicting video? There's been a number of interesting work in that respect. In fact, modern self-supervised methods actually use kind of distortions of images from each other to kind of train the system to kind of figure out that two different views of the same object are actually the same thing, right? And there are also kind of self-supervised learning methods that do not attempt to predict anything. And I'll try to explain sort of a common framework for all of those methods. We see a lot of self-supervised learning methods that are kind of difficult to relate to each other. And I've been seeking sort of a way to kind of understand them and explain them in a sort of a common way. And that approach is called energy-based models. So the basic and I'm sure many of you have heard of this before. So the basic idea of energy-based model is you have a function x of y And it takes two variables. X is the variables that you observe, that you always observe, whether on the training set or not. And Y are the variables that you observe on the training set, but not on the test set. So they are the variables to be predicted, if you want. In fact, in some scenarios, part of Y is also observed, but you never know which part is going to be observed or not. So this is conditional energy-based model, and there are unconditional energy-based models, which are versions where you don't actually have an X, you just have a Y. You're just trying to kind of model Y, and it's internal consistency, if you want. So energy-based model really, so let's imagine that we have, let's say, two variables, Y1, Y2, or we could call them X and Y. That would be kind of equivalent. One is the conditional, the other one the unconditional. And let's say we have data points in that space. Okay, so these are our training samples. What we'd like to learn is an energy function. So a function that gives us low values around the data points on the data manifold, if you want, if there is such a thing, and higher values outside. So I'm drawing the lines of equal energies, if you want. Okay, so we want a groove around the data, and we want the energy function to be higher outside of that groove. Okay, so there's a very easy way to train an energy-based model that doesn't work generally, and that consists in just parameterizing this function f, and then changing the parameters so that the energy goes down is as low as possible on the training samples, right? So take your training samples and just minimize the average energy of the training samples with respect to the parameters of the energy function, regardless of how it's built. This does not necessarily work because if your energy function is very flexible, the energy surface is going to become flat, right? So it may give the same energy to everything, and that's really not a very good model of the dependency between X and Y. So what you really want is the energy outside the data point, the manifold of data, to be higher. And if you have that, that means that if I give you an X or if I give you Y1, you can infer what the likely values of Y2 or Y in the conditional case are in that case, because you just search for values of Y that give you low energy, okay? So an energy-based model can be used to predict or reconstruct by basically finding a Y that minimizes the energy function, or it can be used just to capture dependencies without actually attempting to predict, and that's a very important point. Because there's a lot of architectures that don't even attempt to predict Y. A lot of people who use the word energy-based model, by that mean a probabilistic model whose distribution is defined through an energy function and a Gibbs distribution. My definition is much more general than this. I'm basically, I'm free to use any kind of energy function I want, and I'm not going to necessarily transform it into a probability distribution using the very common Gibbs-Boltzmann distribution, which of course a lot of people know about, and then you normalize your normalization term. So this gives you a normalized distribution over Y, and it's a perfectly fine way of doing it, but I'm not insisting that we'll do this, okay? So this is not, it's a superset of probabilistic models if you want. Okay, so the main question is, how do we train now an energy-based model, right? And there are basically two classes of methods, and those two classes of methods are there to prevent the collapse problem that I talked about earlier, which is that if you simply minimize the energy of the training samples, your energy, there's no guarantee that your energy function is not going to be flat or is going to take some random values outside. Okay, so there are really two categories of methods, and their goal is to make the energy of training samples. So let's say we have a training sample xi, yi. We want that to be less than the energy of f of xi and y bar for any y bar that's sufficiently different from yi. Okay, so that's really kind of the condition, right? And for that, we can design with two classes of methods, right? So the first class of method are contrastive methods. And this is a more general way to use the word contrastive methods than the one people usually use. They usually use this word to designate metric learning or Siamese network type learning where you have two phases. This is more general. This is algorithms that basically push down on the energy of training samples and then push up on the energy of samples outside the training sample explicitly. So basically they differ by which loss function you use. So you're going to have to use a loss function that is going to take into account the energy of a training sample, as well as the energy of, you could think of them as kind of adversarial samples if you want, although that doesn't have much to do with GANs yet. So other points outside the manifold of data whose energy you're going to push up. And they all differ by the form of the L function and how Y bar is picked. So GANs are an example where Y bar is picked by training a neural net to produce the Y bar. That's the generator. And then the energy function is whatever the output of the discriminator is. At least that's called energy-based GANs. But there are other methods. So most methods that people know about, maximum likelihood, for example, that minimizes the negative log of this probability is a contrastive method because it minimizes the energy of training samples that come in the numerator. And then it maximizes the energy of every other sample, and that comes through the logarithm of the denominator. Okay, so probabilistic methods are contrastive methods, most of them. Denoising autoencoders are also contrastive methods. So a denoising autoencoder, you take a piece of data Y, you corrupt it in some way, and you get a new data, which I'm going to call X. And then you train a machine to basically reproduce Y. So I'm using this symbolism where those symbols with kind of a round end are parameterized deterministic functions. And those squares are basically cost functions, okay? So in this case, that measures the distance between the prediction here and whatever comes out here. Okay, so denoising autoencoder is a contrastive method. It consists in taking a data point, corrupting it, and then pushing up the energy of the corrupted version by basically training a neural net to produce the uncorrupted version. And you can show that this will actually increase make the energy of the corrupted sample large. Contrastive divergence, Siamese networks. So basically what people call now contrastive learning, but that's, or metric learning. Those are contrastive methods. The second type of learning energy-based models are so-called regularized methods. And I'm going to hold off a little bit on this before really talking about this. I'm going to come back to this later. So those are methods that essentially guarantee that the energy outside the manifold of data will be high by essentially shrinking the volume of space that can take low energy as much as possible. Okay, they have the big advantage that you don't have to push up on the energy of anything, because pushing up on the energy of stuff outside the manifold of data doesn't scale well with dimension. In a high dimensional space, there are many, many ways to be different from your data, and contrastive methods tend to be inefficient in high dimension. Okay, so how do we minimize the volume of stuff? So let me talk about those regularized methods now. So basically, the motto here is minimizing the volume of Y space that has low energy. Okay, we're going to make the energy of the data point low, but at the same time, we're going to minimize the volume of Y space that can take low energy. So hopefully by that effect, by the side effect, the rest is going to take higher energy, and we're not going to have to push up on anything using contrastive methods. So a good example of this is PCA or autoencoders, that basically, take a Y, run it through an encoder, run this through a decoder, and then measure the reconstruction error between the two. And then you make sure that the internal representation here is low dimension. So because it's low dimension, the volume of space that can take low energy is limited to that dimension, and that constrains that energy. There is a paper that we just presented, my my colleague Li Jing and Yurish Bontar just presented at NeurIPS. It's a technique called IRMA, and that means implicitly regularized, implicitly rank minimizing autoencoder. So the idea there is that you take an autoencoder, okay, you have an encoder and a decoder. And the way you minimize the volume of stuff that can be reconstructed is that you insert here a number of linear layers. The linear layers, they're all, all with different weights. And there was a very interesting work by, various theoreticians that show that if you have a stack of linear layers, the simple fact of training those layers using gradient descent will minimize the rank of the covariance matrix of whatever variable comes out of it. So what you're doing basically is minimizing the effective dimension of the representation. And the more layers you put, the more the effect is strong. So by simply inserting a bunch of linear layers inside of an autoencoder, you basically minimize the rank of the representation. It's as if you were looking for the minimum size representation that actually reconstructs properly. And this works surprisingly well. It's very, very simple. It doesn't work if you add nonlinearities in it. And the reasons for this are not entirely clear. Here's another example, variational autoencoders. So variational autoencoders limit the information content in the code of an autoencoder essentially by adding noise. Okay, so you take your encoder, add noise to the code, run through a decoder. You can write complex math, but in the end, that's what this does. And if you limit the norm of those vectors, or if you make the norm of those vectors as small as possible, because the noise is fixed, or at least cannot be smaller than a certain quantity, the information content that you have in this representation is limited. And as a consequence, the volume of stuff that can take low energy is limited as well. So you can interpret all of those things, and you can write, the variational, the formulas for this in the energy-based framework without any issue. So all of this really is, our interpretations of sort of, can be interpreted in the energy context. Okay, so let me switch page, and I'm not sure why my paper changed. So now I'm going to talk about joint embeddings, and this is, as many of you probably know, a set of techniques that have become quite efficient and popular over the last couple of years. And in fact, Alyosha talked about it. So this is the idea, we used to call these Siamese networks. You take two samples, let's call them X and Y, and you run them through two identical neural net or parameterized function, and then you compute the distance between the outputs. Okay, and so your energy function basically f of xy is equal to something like the square distance between the first function applied to x and the second function applied to y. And in some cases, you force those two functions to be identical. Okay, so that's the idea of the Siamese net. And you need to use a sort of contrastive loss functions to train those things. So for the longest time, those systems have been trained, since the first attempt at doing this in the early 90s. You have two terms, one term that makes the energy small for two pairs that are similar. And so you try to bring the two outputs together. And then you have contrastive terms where x and y are known to be different. And then you push the two outputs away from each other. And you need, again, to have a function that takes into account the energy of your positive pair and the energy of the negative pair. And as in the previous case, and I'm going to call that y bar I, and you could have multiple of those. Sorry, this is not square. This is just a loss function. And what this loss function has to be is that it has to be an increasing function of the energy of the good pair, and it has to be a decreasing function of the energy of the bad pair. And people have come up with dozens of different loss functions to do this, but the most popular one is based on basically plugging a bunch of those y bars into a softmax and things like that. So you certainly have heard about Pearl by Ishan Mishra from last year. MoCo by Kaming He and his collaborators. Both of them are at Facebook, also last year. And then more recently, the SimClear model from Google. All of those models are based on those contrastive methods, but they have a huge problem, which is that training is extremely inefficient because, as I said before, you need to have many, many, many negative samples whose energy is going to get pushed up if you want the system to work relatively well. And by work, I mean you pre-train those systems using this kind of self-supervised learning methods. The way you generate the positive pairs is by generating distortions of images from, say, ImageNet, and then you use the internal representation of that system to essentially as input to a classifier that you train supervised, a very simple classifier, say a linear classifier. So this basically, I think, is running into a wall because of the expense of training those systems. So an alternative emerged really recently with other methods that also use Siamese-like network. One is called Bootstrap Your Own Latent by a bunch of people from DeepMind, as well as an approach from Facebook called Suave by Mathilde Caron at Facebook in Paris, and an even more recent one also by Kaming He called SimSiam, which stands for Simple Siamese. And those have a lot in common. So Suave. So Suave is a little different. This is fairly recent. This was actually presented at NeurIPS as well. But they're based on this idea that you also have two samples that you run through two essentially identical neural nets, and then you add a small neural net called a predictor on top of one of them, and again measure the reconstruction between the two. And with some hocus pocus, one of which involves using batch normalization in the predictor, it turns out you don't need negative samples. So you don't need to have a negative phase to prevent collapse. The fact that there is batch normalization in the predictor essentially has an effect of pushing the representations for each sample away from each other and preventing collapse. A lot of this is not really well understood theoretically yet, so I think there is a lot of interesting work to do there, but it's very interesting. I will end by talking about a class of method that I've been really sort of interested in recently, that are called, that are also kind of regularized latent variable energy-based models. And in the conditional case, the basic architecture is something like this. You have a neural net that you can call a predictor that produces a hidden representation of the observed variables. And then what you want to be able to do is handle multimodality in the prediction. So if you want to train a system to do video prediction and you're predicting the pixels, the main issue with this is that there are many, many ways the video could go and many plausible futures for the video. And you have to be able to handle multiple possible futures. Your model has to be able to represent multiple futures. If you do joint embedding, it's not an issue because the variation of the Y will be swallowed up by the network that they go through, and at the level of representation, you won't have any variation anymore. But if you're going to predict pixels, you need to be able to handle multimodality, and that's what makes it more complicated. So the way to handle this is to have a latent variable, simply. So you have a latent variable Z, and this latent variable takes, this decoder module takes the latent variable and the representation from the observation, and then attempts to make a prediction of the observed variable through, and then you measure the discrepancy with a cost function of this type. And the way you do inference is that you could think of this as computing some energy of three variable, x, y, z, and f of xy can be defined as the minimum over z of e of xyz, right? So I give you an x and a y, and you find the z that minimizes the reconstruction error, and that's the best z, and you use that for subsequent calculation. Now you have an f of xy. You can go back to handling energy-based models the normal way. Okay, so this is a kind of energy-based model, and there are very common algorithms that are of that type. So two examples are k-means. and sparse coding. Those are two examples of kind of energy-based self-supervised learning systems that do not have an X, they're unconditional, but they basically have a latent variable that you have to minimize over to do inference. Is another way to infer the latent variable, which is to marginalize over it. And that would consist in doing the following calculation. So this is what a computation that physicists call a free energy, which is why it's called F. And this basically marginalized over all values of the latent variable and sort of give you a score for how well the model predicts the output. A twist on this is one in which you help the system solve the inference problem, which may be expensive, using something called amortized inference. And the idea of amortized inference is to basically train a neural net or something to predict the optimal value of Z. And so this little neural net, let's call it an encoder, takes into account the representation of the observed variable as well as Y, and it compares the value of Z with its output through a cost function here. And that's part of the energy term. And it's very important that this variable here be regularized through a term that limits its information content, as I explained earlier, because otherwise the system will cheat and basically carry all the necessary information through Z, from Y through Z, back to Y, and the system will not do anything useful for you. So the big question I think that we need to solve in the next few years is, if we are going to use an architecture like this, what is the best method to limit the information capacity of a latent variable? VAEs tell us to do this by adding noise and basically minimizing the norm. We can use dropout, we can use L1 minimization, as in the case of sparse coding, we can use quantization, as in the case of k-means. There's a number of different methods, but I don't think any of them is entirely satisfactory at the moment. And my challenge for the next few years is actually to figure out a good way to do this. I've also talked about the rank minimization method. I think this is kind of a key ingredient that we're missing for making progress. Thank you.
Thank you very much, Yann, for the very nice talk. I'm going to read the questions to you. So the first one is, the energy-based view is a very nice framework to subsume the existing SSL methods. So how can it be leveraged to develop new SSL methods in the future?
Well, so once you understand that the crucial ingredient is how do you make the energy outside of the manifold of data higher, a lot of ideas come up. Okay, so and a lot of ideas that already exist kind of become clear. Become clear why they work. Become clear what ingredients are necessary. So, for example, it was very mysterious how BYOL worked until very recently, until about a month ago, actually. How can you train a Siamese net without actually having explicit negative samples? And it turns out, if you do batch normalization, you have kind of an implicit repelling term between the samples in the batch, and that has the same effect as having negative samples, and it kind of basically prevents collapse. Maybe not very strongly, but well enough that it actually works. You need to have a predictor, though, which is kind of an ingredient that was missing from original Siamese nets. So I think having that picture, I think, brings a lot of new ideas, and it liberates you from the constraints of probabilistic modeling. If we stick to basically insisting that the energy function, for example, be the logarithm of some density, we're shooting ourselves in the foot. For example, let me take a very concrete example. If our data is a thin manifold in a high-dimensional space, the energy that corresponds to this distribution is an energy function that takes some finite value on the manifold and plus infinity just outside the manifold, right? So basically, what this energy function would look like is basically a very narrow canyon around the data manifold. And this is a terrible energy function. It actually is a good probabilistic model of your data. It's a terrible energy model because you can't use it to do inference. If I give you an X and a Y and ask you, if I ask you, is this y a good one, you can compute the energy. But if I ask you, give me another y that is better, you cannot use the gradient of the energy to kind of go towards the data manifold, because your energy function is basically your golf course. And so probabilistic modeling hurts you in that case. The correct answer is bad. Okay, the correct answer is bad. So it's not always the right thing to do. Maximum likelihood is not always the right thing to do.
Thank you, Yan. The second question is the energy-based framework more expressive than others? Or is it looking at other frameworks through different lenses?
Well, so more expressive in the sense, it's more expressive and less expressive. Okay, it's more expressive in the sense that if you write, f of y equals 0, it's a very general, model, right? I haven't specified f, I haven't told you anything. So in that sense, it's general, but it's not very informative. So, so the question is, what are the essential characteristics that make a model, regardless of whether it's energy-based or probabilistic or whatever, what makes it work? And what makes it work is that if you use the energy, if you define the energy the way I did, again, you want the energy on the data points to be lower than the energy outside the data points, outside the data manifold. If you are a probabilist, you say, I want the probability on the data manifold to be higher than outside. But moreover, I want this probability to be a good estimate of the likelihood of the data, of the density. And the point I'm making is that because we're doing estimation in high-dimensional continuous spaces, we have to abandon the idea that we're going to estimate densities in high-dimensional space. That's just too hard of a problem. And so a simpler problem is just to estimate those energy functions without insisting that they are logs of probabilities.
Thanks, Yan. The third question is, there are other types of self-supervised learning tasks, such as the masked token prediction in BERT and also image rotation prediction in computer vision. For those kind of tasks, do you see there will be a general framework to represent them in a unified way?
They're not different. They are included in that framework that I just talked about. So BERT is a denoising autoencoder. It's a particular type of denoising autoencoder, right? You take a sentence, you remove some other word, which is basically a noisification process. It's a corruption process, right? And now you train a neural net to basically reconstruct the original uncorrupted input from the corrupted input. The idea, actually, I had something about this in my PhD thesis back in 1987 for associative memory, but it was better developed by Pascal Vincent and Chobengio, a little over 10 years ago, when they kind of formalized this process. And it, basically it consists, if you think about it, there's many ways to interpret it, but if you think about it, by training a point outside the data manifold, which has been noisify, if you want, to be reconstructed as a point on the manifold, you're telling the system the reconstruction error of a point on the manifold is going to have to be, of a point outside the data manifold, is going to have to be the distance of that point to that manifold. Okay, and so that's implicitly a way of pushing up the energy of points outside the manifold. It's completely interpretable in the context of energy-based models. It's just a denoising autoencoder.
Thank you, Yan. We can take a final question. There are new papers suggesting that the representational space of SSL and the supervised models are very similar, despite they have different cost functions. In your opinion, why they reach to similar representations?
So in fact, they're not that different in the way they train, because if you think about it, the way, for example, all the Perl, Moco, SimClear, BYOL, SWAV are trained, is that you take an image, you distort it, or you distort it in two different ways. Then you run them through two identical neural nets or almost identical neural nets, and then you make the outputs the same if if the two inputs are distortions of the same image, and then you have either those contrastive examples where you feed two different images, or you don't, but you have an implicit term that kind of repels the representations for different samples to prevent collapse. And this is kind of supervised. Okay, it's supervised by data generation. Where we heard a talk right earlier arguing for the fact that a form of self-supervised learning is one in which you generate your training data through data augmentation, and that's exactly that idea. So it's not so surprising that the representations that are arrived at, first of all, are invariant, and second of all, are similar to what you get by supervised learning with a lot of data, because you're basically doing the same thing, but you're doing it without requiring manual labeling. I think there was a very early method proposed by some of my colleagues at Facebook in Paris called NAT, noise as target. So where basically every single sample is its own category, and then the various distorted version of that sample are mapped to the same object. And then you try to maintain targets for each of those, for each of the training samples to be different. And then the SWAV version that I just mentioned that was presented at NeurIPS this year is kind of a improvement of this, where you do quantization, vector quantization, and then you have this sort of interchange of targets, a swapping of target. But it's basically the same idea. And so, you know, it's not that surprising that we get representations that are similar. But I think the use of SSL, as Alyosha said earlier, is broader than just learning representations.
Thank you very much, Yann, again, for this very nice talk and insightful discussions. Thank you, Yann.
Thank you so much.
Our next speaker is Professor Christine Grauman. Professor Christine Grauman is a professor in the Department of Computer Science at the University of Texas at Austin, and a research scientist in Facebook AI research. Her research in computer vision and machine learning focuses on visual recognition and search. She is a IEEE Fellow, Triple AI Fellow, Sloan Fellow, a Microsoft Research New Faculty Fellow, and a recipient of the NSF Career Award, and also the ONR Young Investigator Awards, and also the Parmy Young Researcher Awards in 2013. She is also the winner of the Computers and Thought Award from the International Joint Conference on Artificial Intelligence, the Presidential Early Career Award for Scientists and Engineers. The title of Christine's talk is Self-Supervised Learning with Sight, Sound, and Space. Let's welcome Christine.